Good morning everyone and welcome to these sessions, and the main purpose of this session is to make a revision of the concepts of this particular subject, digital circuits. So we'll go chapter by chapters, like I started with today's class with number systems. Next I'll be taking Boolean algebra, logic gates and so on and so forth. What is the main intention of this particular things is, no matter whether you have learned from me or somebody else or textbooks or whatever the source has. So revision is very important, right? So what I'll try to cover is, what are the key concepts of a particular topic, what are the key formulas, some standard results, and apart from this, some frequently model asked questions. In every year GATE exams, in every topic, in every subject, in every topic, there are some pet questions. When I say pet question, it means okay, in that particular subject, such model of questions are quite repetitive. Or if you go through any particular subjects and if you see the 30 year of papers, you will find certain questions are repeatedly coming. Okay, so I'll try to cover up those all things with respect to number system topic today. And this session is meant for electronics, electrical, instrumentations as well as computer science students. Okay, so what are the various concepts that we have in number systems? So generally, if you have prepared well for GATE exam, you might have started with the number system base conversions. Like one number will be given in some base, let's say base 7 or 6. They will tell you to find its equivalent base 8 equivalents or something like that. So basically it might be something like this. So they will be giving you a number. Okay, so this will be known to you and this base will be known to you, and they will ask you if this is at certain base. So if this is also known to you, then what is these numbers? Right, octal to hexadecimal, hexadecimal to base 7, it can be any base to any base. That is one kind of model. But questions from these segments are relatively less. Okay, in the GATE exam, you'll find less number of questions from these segments. So, but what kind of question we get from the number system topic? So, majority of the questions we are getting from number systems based on the complement methods. Okay. So why complement method is used, or why complement representation is used to represent the negative number without using a negative signs. So because we are dealing with digital subjects, and digital subject is based on binary signal, that is logic 0 and logic 1 in general. So for this number systems, we speak regarding two kind of complements, 1s complement, 2s complements. And majority of the questions, if you see what we are getting from number systems, they are somehow directly or indirectly related to this complement number system concepts. So in this I have taken around 10 to 12 questions. With respect to these all 10 to 12 questions, I'll try to cover up the corresponding concepts as well as the formula. Okay, fine. So let me start with these questions. Okay, the question is 54 by 4 is equals to 13. There are two questions I have given, and the other thing is 135 plus 144 is equals to 323. The question is, what is the valid base? Okay, so in other words, in certain number system or in certain base or certain radix, this equation is valid and this equation is valid. These are two independent questions. Okay, so you can think of like this is question A, this is question B. Okay, at certain number systems this equation is valid, and certain number system this equation is valid. We have to find the possible base. Okay. And that model question I haven't taken because it will be quite boring to tell you again base 2 to base 10, base 10 to base 2, all these numbers instead of conversions I am not taking, because these all things people are learning now from class 8th or 7th standards. So in GATE exam there are some questions, but I believe you know that. So taking that in mind, so let us solve these all questions. Can you respond me? Yes, please try to respond. What is the answer of these questions? So what we do is, in general, we don't know what is the base of this, or basically we have to find the base of this. But we all human beings are comfortable to handle the numbers in base 10 number systems. The number system base can be base 2, 3, 4, it can be any base, but we are comfortable to handle the numbers in base 10, because in day-to-day life, whatever the calculations you are making, so that is in base 10. So no matter whatever be the base of this, so the first step in this case is to convert this into its equivalent base 10 equations. So what I'm assuming is, in this case, what I'm assuming is, let us assume that this entire thing is in base B and this entire thing is also in base B. So this can be equivalent written as 54 base B is equals to 4 base B is equals to 13 base B. So this is the unknown base B, I have to find it out. So what I'll do is, because I am comfortable to handle the equation in base 10 formats, I'll be converting these all numbers into its equivalent base 10. So how to convert a number into its equivalent base 10? So just we have to expand this as a polynomial with respect to B. For example, if I say I have a number 765, this is in base B, what is the decimal equivalence? So this will be given by 7b square plus 6b plus 5 into b power 0, or this is the base 10 equivalent of this number. So using this logic, if I expand this, I will be getting here 5b plus 4, and if I expand this, I will get only 4, and if I expand this, I will get 1 into b plus 3 into b power 0, that is 3. So if you simplify this, you get 5b plus 4 is equals to 4b plus 12. So b is equals to 8. So this is the base, or this equation is valid when I take this base is 8. Okay, or if you want, you can also cross check this. Okay, so if you take these all numbers are in base 8, you may convert that into base 10 and you can satisfy yourself, yeah, whatever the things we have done, that is correct. Okay, just for cross check purpose. So what I am doing is, so you already got the answer 8. Now let us see whether is it the actual thing or not. If I see in terms of base 10, what it will be. If I convert this into base 10, okay, what you will get? You can convert this into base 10. Just like, how do you convert the base B to 10? So like that, if you convert it, 5 into 8 plus 4 divided by 4 is equals to 8 plus 3. So this is 40 plus 4, 44 by 11, 44 by 4 is 11, and 11 is equals to 11, right? So this is in base 8 equations. If I am converting this into base 10 format, I am getting 11 equals to 11. So this is a valid equations. That means this analysis is correct. Okay. Now I hope you understood this, and let us try to solve this question as well. So this is also kind of similar model. So this entire thing is in base B, you can assume. So I can equivalently write this is 135 base B plus 144 base B is equals to 323 base B. So again, if I am converting this into base 10 formats, how much I will get? B square plus 3b plus 5 plus b square plus 4b plus 4 is equals to 3b square plus 2b plus 3. Is that correct? B square plus 3b plus 5 plus b square plus 4b plus 4 is equals to 3b square plus 2b plus 3. So b square, this side if I write 2b square, okay, then 3b plus 4b 7b, and then I have 5 plus 4 9 is equals to 3b square plus 2b plus 3. So 3b square minus 2b square, b square, then 2b minus 7b minus 5b, 9 minus 9 equals to 0. Is that correct? So this is 3, right? This is 3. This is 3. So 3 minus 9, this is minus 6. This equals to 0. If you factorize this, what are the roots you will get? You can factorize these equations and you can get the corresponding roots. So anybody who is solving this, what are the roots you are getting? 3 minus 9, this is. What are the roots you are getting for this? What are the roots of this, please? So you will get one positive root and you will get one negative root for this. Okay, one positive and one negative root for this. So do remember, the base B, this is always a positive integer. Base cannot be negative, it cannot be any fractions, it cannot be a non-integer. You cannot say base is something like 2.4 and all. Okay, So base is always a positive integer. So if you solve these equations, you will get two roots. So whichever the positive root you will get, so that will be a corresponding answer. Just check it out. So this is the end of this question. Okay. So now let us take 6 and minus 1, right? Yeah. So you are getting the roots are 6 and minus 1. So b minus 6 and b plus 1 equals to 0. So that b square. Yeah. So this is the equation we will get. So you will get b equals to 6 and you will get b equals to minus 1. Because I said b is always positive integers. This cannot be the answer. So answer has to be 6. Or if you try to find this, if you want to get its equivalent decimal format, you can check it out. So if you convert this into its decimal forms, the answer of this will be equals to the answer of this. Okay, fine. So this is the end of these questions. Okay. Now let us see the next questions. The next question what I am telling is, number of 1 present in binary representation of the equation is how much? Okay. Number of 1 present in binary representation of these equations. What are the equations? 15 into 256 plus 5 into 16 minus 3. So this is the equations. So they are telling. So this is in what format? This is in by default base 10 format. If no information given, so this is in base 10 formats. So they are asking, so in this polynomial, whatever the answer I will get, if I represent that in corresponding binary forms, how many 1 I will get? So they are asking number of 1 present in binary representation of these equations. So one of the methods some of you may think, so first I will be evaluating the corresponding decimal answer of this, and then I know how to convert decimal into binary, and in that binary I will count how many number of 1s are there. Obviously that is also one of the straightforward approach, but it will be too time consuming, right? So if you get such kind of questions, it's a clue to you this question can be answered in this way, in a faster form you can get it. So I can write this equation as 15 into 16 square, because 16 square is 256, plus 5 into 16 power 1 minus 3 into 16 power 0. So this is something like this. Suppose if you write this is 238 base 10, so this is equivalent to 2 into 10 square plus 3 into 10 power 1 plus 8 into 10 power 0. So this is applicable in any base. For example, if you have a number 7, 2, 3 and this is base is 9, it's given. So its corresponding polynomial representation is 7 into 9 square plus 2 into 9 power 1 plus 3 into 9 power 0. So if this is given, we can write this, or if this is given, we can write back this. So in this case, instead of giving the direct numbers like this, the polynomial is given. From the polynomial, I have just arranged this. Now let us try to write what is the corresponding equivalent numbers. So if you see here, so the expansion is happening in the form of 16 power somethings. So 15 in notation, number system notation, we are telling this is f and 5. So this is f5. What will be the base? The base will be base 16 because the polynomial is 16. Minus, so this I can write this is 0, 3 and this will be also how much? In base 16, right? So you will get this. Okay. So what is the answer then you will get finally? 15 into 56 plus 5 into 16 power 1 minus 3 into 16 power 0. So this if you write it, how much you will get? So this is f and this is 5 and this is 0, 3, 16. If you subtract it, you will get f and you will get 5 minus 3, you will get this is 2. This is in base 16s. If you try to write its equivalent binary form, you will get 1, 1, 1, 1. And if you try to write this, you will get this is 0, 0, 1, 0. So this is what you will get its corresponding binary notations, and if you count it 4 plus 1 5, you will get 5 number of 1 in its corresponding binary forms. Okay. If this could have been plus instead of minus, if this could have been plus, You could have done here plus, then in that case this could have been F5 free and this is base 16, right? And then accordingly you can have convert that into its corresponding binary form by replacing each of this hexadecimal digit by its 4-digit binary equivalent, and again you can calculate that what you will get. Okay, so the answer is 5 for this. Number of 1 present on this is, answer is 5. So you have answered this also. Then the next question I am taking is, the minimal decimal equivalent of 11c base x is how much? What is the minimal decimal equivalent of the number 11c base x? How to answer this? If you have the number 11c base is x, okay, so I am asking its minimum decimal equivalents. Okay, suppose if I say to get its decimal equivalents, as you have seen, so this will be equivalent to x square, I mean 1 into x power 2 plus 1 into x power 1, that is x, plus this is c. What is c? A is 10, b is 11, c is 12. So this is the corresponding decimal equivalent of this. Okay. Now because the word minimum is given, you have to go for the minimum value of x. You have to go for the minimum value of x. Now the concept here what you need is, suppose you have a number n and if you are saying this is b, okay, then it means in this number, or if I say these are so many digits like d1, d2, d3 and so on and so forth. Do remember, if the number is base b, then every digit of this should be in the range of 0, 1 like this up to b minus 1. In other words, if I am saying this base is 6, then I can have the number 2, 3, 4, 5, 0, 1 like this. But if somebody say it is 2, 6, 7, 3, 4 and this is base is 6, this is nonsense, because the base is 6. At max it can contain the number up to 5, not even 6. So this is valid, but this is not valid because 6 and 7 are not allowed if you take the base is 6. Okay. Similarly, so if here what is the approach to get this x? What can be the value of x? Because c value is 12, then naturally it makes sense x value should be greater than equals to 13, because this is containing c, so c is 12. So if it is 12, x value will be at least 13. X value cannot be 12, right, because of this c. So it can, okay, so because there is a general misconceptions, because a, b, c, d, e, f, we make use of these alphabets in base 16 number system. Some people directly assume the base is 16 by observing that c and they find the answer, but that's not correct. In this case, x can be greater than equal to 13. Any base is valid. If I ask you what are the possible base of x, then any value which is greater than equals to 13 is valid for this. And because I need the minimum answer, use the simply take the x value is 13 and you try to solve it. So this is come 169. This is 13 plus 12 is 25 and 4, 9 and this is 194. Right? So this will be the answer, 194. Are you getting the same answer? 194? Yes, please. 194. So the question what I have taken, some interlinked concept also I am trying to cover it up. In case you have missed it, you can still get this concept through this particular questions what I am discussing. So the answer of this question is 194. Okay. The answer of this question was 6 and the answer of this question was 8. Alright. Now let us find what is the gray code of this number 24 which is in base 8 formats. Okay. So we are supposed to find what is the gray code of number 24 which base is 8. Okay. So how do you get it? I hope you know this. Suppose if you have a number, let's say B3, B2, B1, B0. Okay, this is a binary numbers and I am asking you to find its corresponding gray code equivalent. So basically I want from binary so there is some well defined logic for this. You copy this B3 as it is. So this will be your G3. Then you make B3 XOR with B2. What you get, that is G2. You make B2 XOR with B1. What you get, that is your G1. You make B1 XOR with B0. What you will get, that is your G0. So no matter how many bits are there, let it be 10, 20. So this is the standard pattern to convert from binary to gray. So first copy the MSB, then consequently you try making this XOR and you will get the corresponding gray code equivalents. But in this case, the given number is not in the format of what? In the binary forms. So the first step in this case would be, we have to first convert this into its equivalent binary, and then I'll be going through this particular approach. So you know very well how to convert a base 8 number or a octal number into its corresponding binary equivalents. Like just now we have seen how to convert hexadecimal to binary. You have to replace each hexadecimal digit by its 4-digit binary equivalent. Similarly, in this case, each octal digit should replace by its 3-digit binary equivalents. So 2 in its 3-bit format is 010, 4 in its 3-bit format is 100. So this is the corresponding binary numbers. Gray code if I ask you, so 0 will be copied as it is. 0 XOR 1 is 1, so I'll get 1 here, something like this. 1 XOR 0, so this and this you should XOR and you should write the answer here. 1 XOR 0 is 1. Then 0 XOR 1, I mean this and this, you will get it is 1. 1 XOR 0, you will get this is 1. 0 XOR 0, you will get this is 0. Obviously, there are 6 bits in binary forms. In its gray code also the answer will contain 6 bits, because the way we are finding out, the number of bits on binary and gray code will be always equal. So 24 base 8 whose binary was 010100, its corresponding gray code is 0111110. So this is the answer of these questions. This is the answer of these questions. So we are done with this also. Okay. Now the next question is, what are the BCD and Excess-3 code of these numbers? See, these all questions I am taking because these are the kind of questions you are getting in the GATE exam. If you go through the previous year papers, let it be GATE, IS or anything else, you will find such questions. Or basically if you try to go through any questions, that question will be coming on any of these particular models. So if you listen these lessons, so I am very sure like it's a kind of revision, and if you haven't learned the concepts, you can also solve those questions by referring the concept what I am telling now. Next question is, you have to find the BCD and Excess-3 code of a decimal number which is 768.94. 768.94. So how to find the BCD code? BCD code means you have to just replace each of these decimal digit by its 4-digit binary equivalents. Very, very straightforward logic. 7 is 0111, 6 is 0110. Okay. So even if 6 binary is 110, but you are supposed to write 0110. Okay. Strictly it should be 4, not less, not more. It should be 4-digit binary equivalent you should replace. So 8 is 1000, 9 is 1001, 4 is 0100. So this is the corresponding BCD code equivalent of the number 768.94. If you want to get this Excess-3 code equivalent of this, what is the way to get the Excess-3 code? You have to simply add 3 on each of the digits, but make sure like when you are adding 3, you should not take any carry to the next bits. For examples, suppose 768.94, this is the decimal number. I am asking you to find the Excess-3 code. So you have to add 3 on each and every digit. That is the meaning of Excess-3. So if you add it, 4 plus 3 is 7, 9 plus 3 12, 2 that carry 1, that is the wrong approach. Okay. So while doing the addition, you should not take any carry. So 9 plus 3 is 12, 12 stand for 10 is A, 11 is B, 12 is C. 8 3 11, A is 10, B is 11, 6 3 9, 7 3 is A. So this is what you will get. You have to replace each of these particular digits now by its corresponding 4-digit equivalents. If you do that, how much you will get? A stand for 1010, 9 stand for 1001, B stand for 11 1011, C stand for 13 1101, 7 stand for 0111. So this is what the Excess-3 code you will get for this number 768.94. So we are done with this particular questions. Are you following or not? Everything is clear? Okay. So these are some questions I have taken on basics. Now let us take some questions which are from the complement number systems and all. Okay. So now, before I go into these segments, we'll answer this question at the end. Okay. Before that, let us answer this set of questions. So the question is, represent minus 27 base 10 in sign magnitude form, in 1s complement form and in 2s complement forms. This is one of the popular model question in the GATE exams. Okay, some number they will tell you and what will be its equivalent binary representations if this form is used, that form is used, and so on and so forth. Kosika Priya saying C stand for 1100 sir, 10, 11, 12. Yes, 1100. Okay, see. So how to represent this minus 27 base 10 in sign magnitude form, in 1's complement form and in 2's complement form. If I have done any writing these things issue, okay, so if I have not taken C equals to 1100, just take it out. I think you know this A, B, C, D, E, F. So, okay, you can do your own. So let us answer these questions. What is minus 27 in sign magnitude 1s and 2s complement forms? See, the logic to answer such question is, so first you write what is the normal binary equivalent of 27. Okay, just ignore this negative sign now. What is the normal binary equivalent of this 27? So 16 plus 8, 4, then 3. So it will be what? 1, 1, right? So this is the corresponding normal binary form of 27. 16, okay, so you know this, right? 16, 8, 4, 2, 1. If you add the weight, 16 plus 8, 24, 20 plus 26 plus 1, 27. So this is the binary equivalent of 27. Now if I ask you to represent plus 27, so when I say plus 27, if I am emphasizing on the sign, so I mean I am going for the signed number representations. So in the signed number representations, what is the approach to answer the positive number is? So for positive sign, you simply have to attach is 0 because this is the sign bit. For plus the sign bit is 0, for minus the sign bit is 1. Okay. So if it is plus 27, so for this plus I am simply putting this 0, then followed by these numbers 1, 1, 0, 1, 1. So this is the representation of plus 27 in which forms? In sign magnitude form, in 1s complement form as well as in 2s complement form. Do remember, for positive number in all the three formats the representation is same. If somebody asks you represent plus 27 in sign magnitude 1s and 2s form, the answer for all three formats will be same. But the answer for minus 27 in all the three formats will be differing from each other. Okay, for plus 27 this is the logic. Simply find the normal binary equivalents, then attach a 0 on the MSB. So that will be your plus 27. Hope this is clear. Then let me show you how to represent minus 27 in sign magnitude form, how to represent minus 27 in 1s and how to represent minus 27 in 2s. So in sign magnitude form the logic is very straightforward. Like for here in this case for plus you have given 0, so for minus you should give 1. 1 again followed by this bit combination 1, 1, 0, 1, 1. Okay, 1, 1, 0, 1, 1. This is minus 27 in sign magnitude forms. Then if somebody asks you what is the representation of minus 27 in 1s complement form, what you have to do is you have to take 1s complement of plus 27. Okay, so if you take, write this 1s complement of plus 27, what? This is plus 27 representation, right? So this is 0, 1, 1, 0, 1, 1. So you have to take 1s complement of this. If you take 1s complement of this, you know how to get the 1s complement. 0 should be replaced by 1, 1 should be replaced by 0. Right? So this 0 is 1, 1, 1, 0. This is 0 or 1 means it should be 1, 0. So this is the answer of minus 27 in 1s complement form. The same question if I ask in the 2s complement form, the simple logic is instead of taking 1's complement 27, you should take 2's complement of 27 plus 27. So in this case, you should take 2's complement of this number again, which is 0, 1, 1, 0, 1, 1. So how to get the 2's complement directly? I hope you know this. You start copying the bit from the MSB side, okay, unless you get the first one. If you get the first one, after that you replace all 1 by 0 and 0 by 1. For example, if it is 1 here, so in the first bit itself I am getting 1, rest of the bit should be interchange, 1 with 0, 0 with 1. Okay, this is what you will get. Or in simple language, if you have a doubt to get the 2's complement, suppose you have a number 1, 0, 1, 1, 0, 0, 1, 0, 0, 1, 0, something like this. Okay, now if I ask you to find these 2's complements, you start copying the bit from the MSB side until you get the first one. So here I am getting the first one. After these bits, all the bits, after this, every bit should be flipped. So this 0 should be by 1, this also 1, this also 0, 1, 1, 0, 0, 1, 0. This is the logic. But in this case, first bit itself is 1. So I have copied this, then the rest of the bit I have flipped. So the final answer what you are getting is minus 27 in sign magnitude form is how much? This is the answer. 111, 0, 1. 1's complement answer what you are getting is 100, 100. 111, 0, 1. And 2's complement answer what you are getting is 100, 101. Okay. So these are the corresponding answers. Now one thing you notice in this case, okay, so for plus 27 if I ask you, the answer in all three cases will be same, but minus 27 if I ask you, so these all answers are different. Okay, so suppose somebody give you, so 100, 101, okay, so this is in signed representations, not signed number, this is in signed representations. What is the corresponding decimal equivalent? So what is the answer? It's a question mark, we cannot answer. Why you cannot answer? Because as you are seeing here, like for a negative number, there can be three possible answers. So suppose somebody give a particular number, unless until it is not given to you at what particular form it is, whether it is sign magnitude 1s or 2s, we cannot answer such questions. But the main thing that you need to notice is that for negative number in all the three formats, the sign bit is 1. What is the sign bit? The MSB bit is the sign bit. For negative number, the sign bit is always 1. For positive number, the sign bit is always 0. And in all the three formats, positive number representation is same. In all the three formats, negative number representations are different. If you want, you can make your own statements, but these are the corresponding points. Now in this case, one more point I would like to add here. So to represent minus 27, how many bits we have used? We have used 6 bits, right? So we have used 6 bits. In all the three cases, you can see 6 bits. Suppose I ask you to represent this in 8 bits formats, then what is the approach? What is the approach means in 8-bit formats? What is the approach means? It is something like this. In 1s and 2s complements, there is something known as sign bit extension of concepts in 1s and 2s complements. What you need to do is, whatever the sign bit is there, if you copy it 100 times towards left or any number of times towards left, then there is no change in the original value of the numbers. So here the sign bit is 1, okay, 1, okay, you want 2 more additional bit, right? Here it is 6, you need 2 more bits. So those 2 more bits should be, the sign bit should be copied towards left. So this is 1, right? So then 2 times 1 I am taking. Then rest of the bits I am writing 0, 0, 1, double zeros. Similarly in this case also in 2's complement method also. So this is the sign bit, it is 1. You want 2 more bits. I am putting at 2 more ones. The rest of the bits 0, 0, 1, 0, 1 I am keeping as is. Even if somebody say 10-bit representations, you put 2 more ones. Okay. So the point is, if we copy this sign bit any number of times towards left, then there is no change in the original value of the numbers. So something like for plus 27, the number what we have written is, we have written it is 0, 1, 1, 0, 1, 1, isn't it? So again we have used here 6 bits, right? If somebody says you write in 9-bit formats, this is the sign bit, right? You can copy this 3 times towards left, no issues. So no matter whether the number is positive or negative, okay. So in 1s complement and in 2s complement form, if we copy the number sign bit any number of time towards left, then there is no change in the value of the number. So this particular concept is used to what? To extend the bit size of the numbers. There are certain situations where the requirement will be something like this. Suppose you have a 5-bit numbers, you want to make this as a 8-bit number or 10-bit numbers. How to increase the bit size? So normally people think we will be attaching 0. So it will be wrong concept. You cannot attach 0, you should copy the sign bit. If the sign bit is 0, you can copy zeros. If sign bit is 1, you have to copy 1. So this is called extension of sign bits. But who can tell me if I ask the question, so what logic I said, this is for 1s and 2s I said. In 1s and 2s, if we copy the sign bit any number of time towards left, then there is no change in original value of numbers. But what about sign magnitude forms? Very simple logic. Very simple logic. So if this is plus 27 is this much, what is minus 27 is? Because it is minus, so this bit should be 1. Then rest of the bit should indicate 27. Okay. So 27, 1, 1, 0, 1, 1, this is 27. How many bits I have used? 3, 2, 5, 1, 6. And whatever the additional bit you need, 9 bit means 3 number of 0 you should attach. 10 bit means 3 number of 0 or 4 number of 0 you should attach. So 27 is equivalent to 11011. Okay. And this minus is for this one. Okay. So minimum I need 6 plus 1, sorry, 5 plus 1, 6 bit I need. 5 to represent 27. And for the sign bit I need 1 bit. So 6 bit I need. Whatever the additional bit you need, you have to insert in this particular segments. Let it be 3, 4, 5, it doesn't matter. So this is the answer of these questions. So this is a important questions. I hope I have covered all the related concepts. So what are the concept? Let me summarize. First thing, positive number representation in all 3 forms is same. Negative number representation in all 3 forms are different. Sign bit for positive number in all 3 forms are 0. Sign bit for negative numbers in all 3 forms are 1. And in 1s and 2s complement forms, if we copy this sign bit any number of time towards left, then there is no change in original value of these numbers. So this is what we have seen. Now let us see the reverse model questions. The reverse model question is, so this is the question I have taken. Find the decimal equivalent of this number, assuming this is in sign magnitude, 1s and 2s forms. So what is the number I have given? 1, 1, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 0. So this is the number I am given. So my question is, if we assume this is in sign magnitude form, what will be the answer? If you assume this is in 1's complement form, what are the answers? If you assume this is in 2's complement form, what are the answers? So this set of questions what I have written in this column, these questions are quite repetitive and very important questions as far as number system topic is concerned. Okay. So these are, okay, it's coming but not very frequent, but these all questions are very, very important. They are not tough questions, but they are kind of, as I said, we are going to see the repetitive model questions. If you refer 30 years of papers, these are the model of questions you will get. So many times you will find this question has been asked. So this is also one of the very important model questions. Okay. So they will be giving you some binary combinations like this, and if this is in this form, that form, what is the corresponding decimal equivalents? Okay. One thing is confirmed, as we have learned in the previous questions, like for negative number, the sign bit is always 1, right? So no matter whether it is sign magnitude 1s or 2s, for negative number, the sign bit is always 1. So here, the sign bit is 1. So whether I assume this form, this form, this form, compulsorily the answer will be a negative number. So negative sign I am writing for this one. From this one I have sensed this is a negative number. So I am writing here. Then, so if we assume this is sign magnitude form, what you have to do? So as I said, this is sign bit. So the way we have learned the coding technique of sign magnitudes. So rest of the bits you have to find it out, like you have to assume this is a binary numbers and you find the decimal equivalent of this binary numbers. Who can tell me what is the binary, what is the decimal equivalent of this binary numbers? So for this one I am putting a negative sign, and I am left with 1 0 1 0 1 1 0 1 0. So what is the binary equivalent of what is the decimal equivalent of this? So for this one I am putting negative sign. Then you need to find decimal equivalent of the normal binary numbers 1 0 1 0 1 1 0 1 0. 1 0 1 0 1 1 0 1 0. How much will be this one? How much will be this? So this is equivalent to minus of. So you can find it out. How much is the answer? So this is 8 4 2 1. This is 16. This is 32, 64, 128, 256. So you have 256. Then you have 64. Then you have 16, and then you have 10. Am I correct? 8 4 2 1 16 32 64 120 256. 256 I have, then I have 64, then you have 16, and then you have 10. So minus 346. So this is coming minus 346. So this answer is minus 346 in base 10 formats. So this is the answer. Okay, minus 346. So this is the logic to answer if the given number is in what form? Is in sign magnitude forms. This is the decoding technique. We have learned the coding technique. Now I am teaching you the decoding techniques. Now the next thing is, so if this is in 1s complement form, then what is the corresponding answer? Okay, again for this one I am taking negative sign. Then if you assume this in 1s complement form, then this will be given by decimal equivalent of 1s complement of decimal equivalent of 1s complement of this entire number. Entire number is 110 101 1010 110 101 1010. So decimal equivalent of 1s complement of this number. So this is equivalent to negative of decimal equivalent of, if you take 1s complement of this, 0 0 1 0 1 0 0 1 0 1. So this is 5. How much will be this much? How much is this one? 8 4 8 4 2 1 16 32. This is 64. This is 128. So 128. Then you have 32, and then you have 2. How much will be this? This is coming 162. Is it 162? So this answer, if it is 162, so this will be minus of 162. Okay. So the standard method is, if you know this is in 1s complement forms, then what you can do is, okay, so this is the methods. So it is 165. Let's see. 32. Okay, this is 5, right? Yeah. This will be 165. Sorry. Yes, this will be 165. Yes, this will be 165. Minus of 165. So this is the answer. So the standard method is, if you know this is 1s complement form, so take the sign bit. For sign bit you put a negative sign, then decimal equivalent of 1s complement of the entire numbers. So you can find the 1s complement by replacing 0 with 1, 1 with 0, and then if you take it's a normal binary numbers, and if you find decimal, so you are getting the answer is 165. So this answer is minus 165. And finally, if I assume this is in 2's complement form, then what will be the answers? So the logic is again very simple. The only change what you have to make is, instead of finding 1's complements, you should take this is 2's complements. Okay, so you should find the 2's complements. So you find 2's complements, you can find it out. So 0 0, then I am getting the 1 here. So I am copying the bit till I get the first one. After this, all bits should be flipped. So this is 0, it is 1, double 1 will be double 0, 0 will be 1, 1 will be 0, 0 will be 1, and then I'll have double 0. You can find it on how much it will be. This is 8421, this is 16, this is 32, this is 64, this is 128. So 128 plus 32 plus 6. So this will be coming 166. So the answer will be minus of 166. Right? So this answer is minus of 166. Minus of 166. Okay. So in sign magnitude form, answer is minus 346. 1s complement form, answer is minus of 165. And in 2s, it is minus of 166. This is the answer. So that's what I was telling. Unless until you don't know which particular format this is, whether it is in 1s or 2s or sign magnitude, we cannot tell the answers. So if somebody says signed representations, it indicates all the three formats. But if somebody is saying specifically, then it can be any of this. So unless until we don't know what format, we cannot tell the answer uniquely. Because for the same representations, we are getting three different answers. So unless until which category is not specified, we cannot tell what is the right answer. So the answer is minus 346, minus 165 and minus 166. Now let us take this question now. Using 7 binary bits, what are the largest positive and negative numbers that can be represented using unsigned binary forms, sign magnitude, 1s and 2s forms. So I am just giving you these formats. Using n bits, okay, in the normal binary form, the range is, because normal binary forms we represent only the positive numbers, 0, and the largest number will be 2 to the power n minus 1. Okay, 2 to the power n minus 1. Suppose for example, if I say 4 bits, when you take 4 bits, so if you take all bits are 1, if this is in binary form, a decimal equivalent is 15, which is 2 power 4 minus 1. So in normal binary forms, if you are using n bits, the range of the numbers that you can represent is 0 to 2 power n minus 1. If you are going with sign magnitude form, okay, then the negative number is minus of 2 to the power n minus 1 minus 1 to plus of 2 to the power n minus 1 minus 1. So this is the range of numbers if you are going for sign magnitudes, and even in the 1s complement, this is the same range. For 1s and sign magnitude form, these are the numbers that we can represent. But if you are going with 2s complement forms, so it is minus of 2 to the power n minus 1 to plus of 2 to the power n minus 1 minus 1. So these are the ranges numbers. So there are again logic how to get the corresponding answers. Okay, but these are some of the standard formula you should practice. So because here I have given 7 binary bits, so n value equal to 7, you can substitute 7 and you can get the answers. So this is the largest positive. The question is, using 7 binary bits, what are the largest positive and negative numbers that can be represented? So in this case, there is no scope for negative numbers. So negative number we cannot represent. Positive number will be 2 power 7 minus 1. You can check it out how much the answers. And if they ask for 1s and sign magnitudes, so if you substitute here n equal to 7, so this will be 6 and this will also be 6. Similarly, this is also 6 and this is also 6. So these are the largest positive numbers and these are the largest negative number in its corresponding forms. One is sign magnitudes and 2 is complement forms. So this is also repetitive model questions. Now the next question I am going to take is, 0 have unique representation in which forms? Sign magnitudes, 1s, 2s, or in all of them. Okay. See, actually there is a concept called plus 0 and minus 0. Suppose 0, if I ask you to represent, so it is 0, 0, 0, 0. Suppose I am telling you for 4-bit cases. or 3-bit cases. In 3-bit, 0 is simply 0, 0, 0. This is in normal binary forms. Now if I ask you to represent plus 0, so if I say plus 0, so for plus we'll add one sign bit 0, then we'll have triple zeros. So this is in sign magnitudes 1s and 2s, just like we have seen for plus 27, this is plus 0. Now if I say what is minus 0, okay, what is minus 0 in sign magnitude form, what is minus 0 in complement form, what is minus 0 in 2's complement form. We know practically there is nothing called plus minus 0, but if I say it is what we will get. So minus 0 if I say, so 0, for 0 I have used 3 bits. For minus we will be putting 1 here. So this 1 is meant for the sign bit. So this is the representation of minus 0 in sign magnitude forms. And if I ask you to represent minus 0 in 1's complement form, so then this answer will be 1's complement of plus 0. Yes or no? Like how to get the minus 27, I have shown you how to represent minus 27 1's complement forms exactly in the same way. So if I ask you minus 0 in 1's complement form, so you have to take 1's complement of plus 0. So this is your 1's complement of plus 0 is 0, 0, 0, 0, right? Plus 0 is 0, 0, 0, 0. If you take 1's complement of 0, 0, 0, 0, the answer what you will get is 1, 1, 1, 1. You will get it is 1, 1, 1, 1. So the conclusion is, in sign magnitude form, plus 0 is 0, 0, 0, 0 and minus 0 what you are getting is 1, 1, 1, 1. If I am going for 4-bit formats, 0 in normal binary 4 is 0, 0, plus 0 is 4 zeros, minus 0 in sign magnitude form we are getting it is 4 ones. So 0 is treated in two different ways, plus 0, minus 0 separately in sign magnitude forms. Now what will be happening in case of 1's complement form? If you go for 1's complement form, so what is plus 0 and what is minus 0? So plus 0 is again 4 zeros, because plus 0 it will be same in all three formats. Now if I say what is this, so sign magnitude form we have already seen, right? 1 triple zeros. In 1's complement form we have seen 1, 1, 1, 1. Yeah, sorry. So this is in 1's complement forms. So in sign magnitude form, plus 0, minus 0 representations are different. 1's complement also it is different, because plus 0 is separate and minus 0 is separate. But what in case of 2's complement form? So how to get the 2's complementation of this minus 0? So in this case what you have to do? You have to do 2's complement of plus 0. So that is 2's complement of 0, 0, 0, 0. So if you take 2's complement of this, if you start copying this 0, 0, 0, 0, because you are not getting 1, so you will be copying it till you get the first one. So if you are not getting any 1, you have to copy it as it is. So basically this is the answer you are getting, 0, 0, 0, 0. So what you are finding is, in 2's complement form, plus 0 is 0, 0, 0, 0, minus 0 is also 0, 0, 0, 0. So the conclusion is, 0 is represented uniquely. I mean plus 0, minus 0 are treated same in case of 2's complements. But plus 0 and minus 0 are treated in different way in 1's as well as in case of sign magnitude form. So the question is, 0 have unique representation which of the format? The answer is 2's complement. Not in sign magnitude, not in 1's, because sign magnitude 1's they have two possible representations. In fact, that's the reason why in case of 2's complements we are able to represent one extra number compared to these formats, right? If you compare this and this, we are getting one extra negative numbers. And why is it happening? In this case the number 0 is occupying two places, but in this case 0 will occupy one place. That's why we are getting one more additional bit combinations. Okay, so this is the answer of this. Now we are left with this and these questions. Let us answer this. So first thing is, what is the concept of overflow? What is the concept of overflow? So overflow concept is something like this. If you are adding two same sign number and in the answer you are getting the opposite sign number, we say overflow has happened. For example, it is quite impossible, like if you are adding two positive number, is it possible that you will get the answer negative number? Or if you are adding two negative number, is it possible that you get the positive number? Not possible. We expect if we add two positive number, my answer should be positive. If I add two negative number, my answer should be negative. But in reality, if you don't use sufficient number of bits, then you get this magic, like you add to positive number, you get negative number. You add to negative number, you get positive number. These all things happens. Okay, let us see. So, see, read the question carefully. In which of following 2's complement additions, in other words, I am interested for 2's complement additions, overflow will happen if 4 bits are used. See the questions, 4 bits are used and 2's method is followed. Okay, the addition is happening using 2's complement methods and 4 bits are used. Okay, see, 6 plus 5, this is equivalent to plus 6 plus 5. So, plus 6 representation is 0, 1, 1, 0. Actually, 6 is 1, 1, 0. Because of this plus, you will get 0 here. So, this is 0, 1, 1, 0. And then if I say plus 5, it will be 0, 1, 1. It will be, sorry, 0 and this is 1, 0, 1. Plus is for 0 and for 5 I have 1, 0, 1. Now, if I add it, what is the answer I will get? I will get here 1. I'll get here 1, I'll get here 1, 1, 0, carry is 1, okay. So, I'll get here it is 1, I'm getting it is 1, 0, 1, 1. So, this is the answer I'm getting. So, I have added 6 plus 5, I'm getting this answer. But this answer, you know, this is in 2's complement form. So, if you have learned the addition using 2's complement formats, so this is in 2's complement form. So, if it is in 2's complement form, then what is the corresponding decimal equivalence? Like I have solved these questions, if this number is in 2's complement form, what is the decimal equivalent? I have told the logic how to get it. So exactly the same way. So if this is the corresponding answer, it is in 2's complement form, then please let me know what is the corresponding decimal equivalents. Now one thing is confirmed, if I am adding 6 plus 5, I expect my answer should be plus 11. And what is the representation of plus 11? 11 stands for 1, 0, 1, 1. Plus means it should be 0. So I expect the answer should be 0, 1, 0, 1, 1. But here I am getting it is 1, 0, 1, 1. So first thing, by observing the number, if it is in 2's complement form, this is a negative number because the MSB or the sign bit is 1. So it's a negative number. Okay. And if you see it is in 2's complement form, if you find it, so you have to find the decimal equivalent of 2's complement of this number. If you find the 2's complements, so this is 1. Then it is 0, then it is 1, then this is 0. So you will get this is your plus 5. So this answer is basically indicating plus 5. So in other words, you are adding plus 6 and plus 5, but as per the addition method, so your answer is again you are getting this is plus 5. So not plus 5, sorry, minus 5. Because it's already minus, right? So this is minus 5. So this answer is minus 5. Okay, I mean only this is 5, but because of minus, this is minus 5. Exactly the same method what we have adopted for this. In fact, this much of drama is not needed. By observing this itself, you can tell. So if the sign bit is 0, sign bit is 0, but the answer of the sign bit what you are getting is, it is 1. So this is overflow is happening. Simple logic, how to identify this answer directly. The main root cause of the overflow is we use less number of bits. Whenever we use the less number of bits, then we get the overflow. Okay. So see here one thing. To represent plus 6, how many bits we have used? 4 bits. To represent plus 5, how many bits we used? 4 bits. What is the expected answer? Plus 11. For plus 11, how many bits are needed? For 11 you need 4 bits and for the sign bit you need 1 more bit. So that is you need here 5 bits. So your expected answer is requiring at least 5 bits, but you are using 4 bits. So obviously that 4 bit will not be enough to hold the corresponding 5 bit answers. So that's why this is called overflow. In other words, in that much of bit combinations, the corresponding answer is getting overflowed. It is not able to getting holded in that particular segments. Okay. So if you understood this logic, now without doing all these things, directly you should be able to tell me in what cases we will get the corresponding answers. I mean, what case overflow will happen, what case overflow will not happen. What do you think, in case of second bit overflow will happen or not? In -5, -4, overflow will happen or not? To represent -5, how many bits are needed? Because +5 representation is, 5 is 101, +5 is 0101. So -5 means you have to take the 2's complement of this. If you take 2's complement of this will be 1, this is 1, this is 0, and this is 1. So how many bits we are using? We are using 4 bits. Similarly, to represent -4 also we will be using 4 bits. But what is my expected answer? My expected answer is -9. If I add -5 and -4, my answer is -9. To represent -9, how many bits are needed? So 9 is 1001. So +9 is 01001. -9 is, you have to find the 2's complement of this. This is 11101. So to represent -9, you need here 5 bits. Again the same story. So originally we are using 4 bits, but my expected answer needs at least 5 bits. If it needs at least 5 bits, so naturally 4 bit will not be enough to hold this particular 5 bit answer. Even in this case also you will get overflow. So you will get overflow here, you will get overflow here. But what in case of the remaining 2 bits? So to represent, so next thing is, so the next 3 options is 4 minus 7. So 4 minus 7 equivalent to +4 minus 7, or which is +4 plus of -7. Okay. Now what is +4? To represent +4, how many bits I need? So 4 stand for 1 double zeros, +4 stand for 0100. Okay. So -4 stand for 0011, right? Okay. So to here, so we are using to represent this +4. I don't need -4 in this case. In the next case I need -4 in the D bits. But to indicate +4, okay, to indicate +4, so for +4 I am using how many bits? 4 bits, right? +4 I am using 4 bits. Then I am doing -7. So 7 is 111, +7 is 0111, -7 is, if you take 1's complement, 2's complement of this, because we are going for 2's complement methods, 1001. 1 we have copied, the rest of the bits I am flipped. So this is, we are using here 4 bits. 4 bits. But what is the expected answer? Expected answer is 4 minus 7 is -3. So what is -3? So 3 is 11, plus 3 is 011. -3 is, if you take 2's complement of this, 1, then 0, this is 1. So I need minimum 3 bits. You need minimum 3 bits. So your answer is expecting 3 bits. You are already using 4 bits. So obviously in this case, you are not going to get any overflow. And one common sense is this: if we add 2 opposite sign number, we will never get overflow conditions. One positive number, one negative number, if you are adding such combinations, you are never going to get any overflow, because whatever the answer you are going to get, so those many bits would already be having used to represent these individual numbers. So in such cases, only for illustration purpose I was showing you. But in general, if you are adding 2 opposite sign numbers, you are never going to get overflow. You may get overflow if you are adding 2 same sign number. Okay, 2 same sign number. Why I am using the word may? So with respect to 6 and 5 I have shown, overflow is happening. But suppose instead of 6 and 5, if I am saying 6 and 3, then what do you think? Still the overflow will come? Are you getting what I am asking? If I am saying +6 +3, in this case, my expected answer is +9. So here I have added 2 same sign number, 6 and 5. I got the opposite sign number, we said overflow is happening. But now I am giving you again 2 same sign number, but 6 and 3. In this case, will overflow will happen. So 6 plus 6 is 0110, and plus 3 we have already seen, it is 011. Okay, 0, 1, 1. And because if we are using 4 bits, the sign bit should be copied. The sign bit is 0. If I copy it one more time, so this will be the corresponding 4-bit representation of plus 3. Okay, if you add it, you get 1, 1, 1, 0, carry is 1, 1, 1, 0, carry is 1. Yeah. So yeah, in this case also it is happening. Obviously it's happening because to indicate plus 5, plus 9, we need 5 bits, right? 5 bits. Why? For 9 it is 1001 and one more sign bit. You need 5 bits, but we are using 4 bits. My intention is, let us say, if I am saying you take plus 5 and you take plus 2. In this case you can see there won't be any overflow. Plus 5 is 0, 1, 0, 1. Plus 2 is 1, 0, and plus 2, 1, 0 is what? 2. Plus 2 is 0, 1, 0. If you need 4 bits, you have to copy the sign bit. So this is what you will get. So the expected answer is plus 7. And if you see 1, 1, 1, and this is 0. So this is also indicating plus 7 in 2's complement formats. So you can see if I am adding here. So if you are adding here, you can see 0, 0, and this is also 0. But in this case 0, 0, here we got it is 1. So in this case, no overflow is happening. In this case, overflow is happening. So that's what I wanted to tell. If we add two same sign number, there is a chance that overflow may happen. It will not happen, I cannot guarantee. It depends on what numbers you have taken. But if you are adding two opposite sign number, you are never going to get these overflow conditions like these cases. So here there is no overflow. What about minus 3 and minus 4? Can you tell me? What about minus 3, minus 4? Overflow will happen in this case or not? For minus 3 and minus 4, overflow will happen or not happen? Can I get your response once? For minus 3, so I am saying to use 4 bits because in the questions I said use 4 bits. For minus 4 also, you will be using 4 bits. Your answer, what you are supposed to get is minus 7. So to represent minus 7, how many bits are needed? 7 stand for 1, 1, 1. Plus 7 stand for 0, 1, 1. Minus 7 stand for, if you take the 2's complement of this, 1, 0, 0, 1. So you are again need to represent minus 7 4 bits. So you have already used 4 bits, 4 bits. In this case also your answer needs 4 bits. So again, because there is no mismatch, so there is no chance overflow will happen. So in this case also overflow will not happen. But what do you think? If I make this is minus 3 and minus 6, in this case overflow will happen or not? In this case it will happen. Why? Because in this case your answer is minus 9. To represent minus 9 you need 5 bits. Your answer need 5 bits, but you have used 4 bits. So definitely overflow will come into pictures. So you have answered this also. And we are left with the last one. What is the overflow logic expressions? See. So the logic expression is something like this. If Cin indicates carry into MSB and Cout indicates carry out of MSB, okay, then if Cin XOR with Cout, if this happens to be 1, this will indicate overflow, and if this will be 0, then it is no overflow. No overflow. Like in this case. So in this case overflow is happening, we concluded, right? So I am defining two variables, Cin and Cout. Okay? So Cin in this case you can see is 1, right? Cin in this case is 1. I mean carry into MSB. So this is the carry. So this is what is your Cin. But in the final addition, are you getting any carry out of MSB? You are not getting. So basically your Cout in this case is 0. If there would have been, let's say if this is 1, this is 1, then sum is 0, carry is 1. So in that case you are getting Cout also 1. But in this case we are not getting any Cout. So Cin is 1, C out is 0. So 1 XOR 0. So you get it is 1, and if you are getting 1, that is overflow. That's what we said. Now suppose if you want to do for minus 3 and minus, okay, so let's say for what? For 4 and minus 7. So in this case we said there is no overflow. Then let's see how there is no overflow. Four and minus 7. So plus 4 is 0, 1, 0, 0. And then we said minus 7. So plus 7 is 0, 1, 1. Minus 7, if I ask you, have to take 2's complement. This is 1, then it is 0, 0, and this is 1. If you add it, 1, 0, 1, and you are getting it is 1. Right? So I am claiming in this case there is no overflow. How? Because if I see here, so are you getting any carry to this? No. So C in is 0. And even I don't see any carry coming out of this. So basically C out is also 0. So if both C in and C out are 0, so 0 XOR 0 is again 0. If there is 0, then there is no overflow. So in this case there is no overflow. And you can take any cases. For example, minus 5 and minus 4 if you take. So minus 5, what is the representations? So plus 5 is 0, 1, 0, 1. Minus 5, you have to take 2's complement of this. You get 1. Then for this, you get 1, 0, and 1. This is minus 5. And minus 4 if you do, so this is, you will get this. This is minus 4. So if you add it, you get 1, 1, 0, 1, 0, 1, 1, 1, 1, 0, and carry is 1. But in 2's complement, this carry is discarded. So in this case, you can see this is 1, 1, 0, 1, 1. So here we are not getting any carry to this. So basically C in this case is 0. However, we are getting C out, right? We are getting this one, we are discarding this carry. So they are getting C out equals to 1. So C in is 0, C out is 1. So 0 XOR 1 is 1. So it indicating, because we are getting 1, it is indicating overflow condition, and you can see also. So the sign bit of this is 1, sign bit of this is 1, but sign bit of this is 0. So basically it is telling we are adding 2 negative number, but we are getting a positive number, which is a pakka case of overflow. So this is the overflow logic expression. C in XOR with C out, if you get this is what? 1, then it will indicate overflow. If it is 0, then there is no overflow. So this is what is the discussion I wanted to do with respect to number system and binary code topics. So before I started these sessions, I have assumed that you have some basics of the number system you have learnt, and this is just a revision series, and these are the kind of questions what we are getting in from the GATE exam or any other exams. Just go through the concept what I have discussed, and that will be good enough to answer all the previous year questions. And do let me know your comments. And by the way, I will be covering most of the topics of this particular course one by one. But meanwhile, if you have doubts or if you want to have some sessions on one particular topic, do let me know. We will conduct the session with respect to that. So thank you for watching this video. Thank you everyone.